So I have the privilege of chairing the closing session and giving the first talk. So being relatively new to this field, I was nearly used up too much of my material yesterday. I'm going to try and show you some different stuff that's radically different from before. Well, there's two things that I want to do. Like, first of all, we have made some progress in yesterday. So in terms of some results that we weren't happy with and wasn't given results that we expected, has been fixed. And since this is all supposed to be about getting maximum performance out of the machines, then I'll just update you quickly on what those results actually look like. And then I'm going to also talk about some of the more exotic stuff that we're doing, focused on unstructured meshes. And I guess one of the things that I want for this particular talk is I think that it should be largely discussion. So it should be informal. I'm happy to stop in the middle and go off in tangents because certainly I think a lot of the techniques that we're proposing here, the methods we're proposing on at least trying out here, it's highly speculative. And they either might be very important or entirely unusable for this particular application. So I think that'll be interesting. I know we've already had some interesting discussions about this. Oops. So what you'll see here is some of the slides are the same, except now I've added in some extra detail. I've shown you a small bit more extra detail in what we're doing in some other directions. So from a physics point of view, it hasn't changed. Like, we're still solving the same PDEs, but as I was emphasizing earlier on, to really make progress with this problem, it's not enough just to look at one numerical algorithm and look at trying to optimizing it on the computer. We also have to look around and say, okay, maybe we have to change the actual numerical algorithms to get the most out of this thing. So the first slide is still all the same, except I took my corrections here from Felix. So rather than a naive estimate of times 20 factor and expense is potentially like a factor of 1,000. Okay, so in fact that's great news for me because it generates lots of work. Okay, so and we all like research. Causes a headache for the industry guys, but they just gotta have to hand over more money for us to figure out this problem. And a lot of the story here now, you'll see it's the same. So look for commonalities because there's a similar philosophy going through this. So you already heard yesterday talking about finite difference, so taking a very standard approach. And the algorithm trick here, of course, as everyone knows, is go to high order. And then as we talked yesterday, we know why that's advantageous also from a computer perspective, because it's increasing parametric intensity and allowing vectorization, as well as coarser grid and so on. Now, in fact, then there's also scope for doing this on an unstructured mesh. And I know that lots of people in the community, I've read various theses from people that were doing FWI, and they did look at finite element methods. And it's important to remember that very often people are only looking at low-order finite element methods. And if you compare a low-order finite element method to finite difference, the finite element method is going to look terrible. Okay, it's low order. It's got it's completely memory bound, and you only achieve a very low percentage of the peak performance of the machine. Like, you know, something around 5% of peak performance is typical. So like, this is why this discouraged an awful lot of people from even considering using this for like wave type simulations. But in actual fact, the solution is to do the exact same thing as what the solution was for finite difference. What you have to do is you have to move to a higher order as well. So there's a bunch of really good high order schemes. So I mentioned two of them here. Like, the two key codes, I think, are SciSol and SpecFim 3D. So both of these are from the global seismic community, you probably know. And just to show you like how good these are from numerical efficiency point of view, there's an annual prize that's given out for the maximum number of flops, like, you know, that's achieved in a computation. They call the Gordon Bell Prize. So this is the big prize to get in supercomputing. And Sisal, it was either the winner or a runner-up last year. So they achieved a very high performance. And they were achieving something like 80% of peak performance of the machine, something really, really high. And it is because of these techniques. It is higher order. And then they use, like they're replacing time derivatives with spatial derivatives. I think you see some methods in finite difference doing something similar. So they get a lot out of it. So the key take-home message here is, yeah, if you learned, okay, we had bad experiences with finite element, like you have to reconsider this in a new light. Yeah, low-order finite element is bad. It's going to be bad for everyone. Like I think an awful lot of the CFD community is in trouble because they like to stick to these types of low-order schemes on finite element or finite volume. And the reality is they're going to be performing worse and worse and worse as computer architectures evolve. So you have to go to higher order. And the other point then, like, why would you go, well, still a valid question, why would you bother at all with it? Like, is there anything else? Well, the other thing, of course, is that if you've got an unstructured mesh, there could be scope for efficiencies there. If there's parts of your domain that are not very interesting or homogeneous, you can use very large elements. If there's other places that are rapidly changing that have got a lot of detail, you have small elements. So if you like, there's a certain amount of, you're trying to be frugal, if you like, about the numbers of your use of degrees of freedom in your system. And then, of course, if you take that step, it's only another small step then to start using some type of error measures or like a residual or some measure of the error in your solution, whether that be your model or whatever else. Like you can define how that best should look like, and then use that as a guide to decide, well, what is an ideal mesh for this particular problem? And you can be as conservative as you want about that. And then you have to recognize this as a dialing. It's not an all or nothing. You go from having something that's very fine and resolving to start to adjust the dial to something that's coarser. So there's room there for some experimentation, and I think plenty of open questions. Of course, like with all of these numerical methods, the other very good reason why not everyone has done this and why these things haven't been tried is, yeah, there might be good ideas, but they're pretty difficult to implement. So we already talked about finite difference yesterday. Like it can be quite a lot of labor to start developing various different higher order schemes. And the story only gets worse. There's much more software associated with implementing unstructured meshes. And there's much more software associated with working out adjoints for this, doing automatic differentiation for this. And there's also, like, there's more open questions here. Like already there's lots of experience with adaptive meshes for elliptic type problems. Even for elliptic type problems, there's still only a few groups in the world that have got significant experience of this and got it working. And it's going to be more difficult probably for hyperbolic problems because I think there's likely to be lots of problems of getting spurious reflections. Like once again, lots of unknowns. And the other issue as well is, of course, parallel implementation of adaptive methods is not for the faint-hearted. So I can vouch for this. Yeah, sorry, I should have explained that. So yeah, elliptic problems like CFD are a lot more forgiving. Hyperbolic problems such as the wave equation are far less forgiving. No, correct. So the way that you should view this is that it's like a dial. So you can use it as much or as little as you want. And I think really what's required here in terms of how you should use it, then I think that's exactly, like we've that well figured out for CFD, these types of problems. Of course, we have to develop the experience here to know where's the optimal place to put it. Like what we have put a huge amount of effort into in this is, so this is like my my parallel existence was implementing, actually re-implementing this from, is Adrian here? Oh yes, there. Like say, Adrian in his previous life was the original person to implement adaptive methods for our research group, and have since been re-implemented using lots of fine-grained parallelization techniques to speed it up a lot. So this we can adapt a mesh now, like that might have a million elements in a couple of seconds. But at the same time, you don't want to do that in an inner loop or while you're propagating a wave, because you'll get lots of spurious numerical issues. However, moving it out, only using it maybe at the beginning, so maybe you only adapt the mesh to the initials, to the initial solution given, or maybe just moving it inside the outer loop and the optimization, like those are the things that could be reasonably played with, because the overhead would be low and the type of dispersion effects that they would introduce as a solution would be minimized. Like you would be able to control it in some formal way, because all of this is, like in some of the literature, they refer to this as error control. So that gets you a better idea of what you're trying to do. You're putting a dial on your discretization errors. So once again, like I encourage people to interject on this, because like you'll appreciate here there's a lot of speculation going on. As in, we've got an interesting hammer, and it's not quite clear if we could apply. So it depends on different problems. What's the optimal thing to do? So the simplest thing that you could say is, okay, well, let's say we're going to define our error as linear interpolation error. So then that allows, so then you work out your linear interpolation error. So given a mesh and given a particular field, you want to control the linear interpolation error. So you're truncating a Taylor series. Yes, because it's in this particular case, in the case that I'm using, the assumption is that it's that your error is dependent upon the curvature of your solution. So what you're doing then is that your dial now is only making sure that, so that in that case, if you have got high curvature, it'll give you small elements. And if you have got no curvature, you have very large elements. And you can sort of have some type of gradient of element size between those two things. But it's not your only error metric. There's actually a whole family of error metrics that people apply. And it depends very much on the nature of the problem. So it depends on you understanding where you're really incurring errors in the problem, and then using that to decide what your error should look like. So maybe I should have added some extra slides for that. But I think one thing that's always very good to keep in mind when we're talking about adaptive methods is that there's effectively two inputs. So you have the input mesh, but the other thing that's much more important is actually a field that describes in some way like what kind of a mesh that you require ideally to minimize errors or to control errors in some mathematically rigorous way. And actually the fact is, in the literature, the most sophisticated error metrics are actually based on adjoint methods. So it might actually be that you have, and that's a real problem for a lot of the CFD community, because they don't already have an adjoint. And so that's really hard work that they suddenly have to calculate this. So it might be that you have a head start for this kind of a problem, because you already have access to the adjoint, which tells you a lot about your errors. Some people do. So those that do have a head start, as we rephrase it. So once again, that's on like keeping my split between opportunities in physics, numerical algorithms, and compute. Like so, this lives very much on challenge 2. And in terms of challenge 3, then is from a computing perspective, this largely doesn't change. You've pretty much got all the same problems that applied for problems and opportunities that applied for finite difference also exist for finite element, and you're trying to also leverage the fact that if you go to higher order, this lends itself to vectorization, which is really important for performance. Not only that, but when you go to higher order methods, and this is particularly true for a lot of discontinuous Glerkin type schemes and higher order schemes, is you get a lot more data locality as well, which is extremely good for optimizing. And it's exactly the kind of thing that modern computing architectures need, so this is all good. And then the next thing here is, we'll get onto this later on, there's also DSLs that have been defined for finite element methods. So the same way as we're using stencil compilers and DSLs for finite difference, there's also a large community that develops DSLs specifically for finite element. So we get to stick to our same philosophy as well of automatically generating code. So there's a certain amount of mirroring here of strategy. So let me skip over the stuff that's irrelevant that we covered yesterday. So this is. So the only thing that I wanted to say, the reason I left in these slides is I just wanted to quickly go back to yesterday's talk. So if you remember it, one of the things that I was really unhappy about, because we're actively working on this, someone actually downloaded our code yesterday and was having a quick go through it and all the rest. So the health warning I had is that we're actively working on this quite hard, and we were updating these results. So yesterday I was really unhappy because there seemed to be a very big gap here, and I wasn't sure why our performance wasn't so good. We figured out this morning that it was actually, this number was wrong because it was miscalculated, so that has been adjusted. So now what we're quite happy about is we're achieving, like when we worked out what the theoretical peak is for this particular numerical algorithm, so this is a fourth order scheme, so this is the theoretical peak, this is our achieved performance here when we actually measured it. So we were then 60% of the theoretical peak performance for that algorithm. So that's pretty much what the Intel engineers will tell you is as good as you're going to get. And so we're very happy with that. And the exact same thing is true then for the phi. So once we adjusted this number, like once again we're getting to within 60%. And then just to revise on our lessons yesterday, the only way now that for finite difference, the only way that we can improve upon this is we have to get this line and we have to shift it in that direction. And the way that we shift it in that direction, so this is for a fourth order scheme, and trying to figure out from other finite difference methods and what I could find in the literature, if we move up to an 8th order scheme, we should be hitting around 2. So that'll bring us around there. That's what we should be aiming for. And I still have to sit down and look. There's a I believe a 12th order scheme, isn't it? Is it a Chevron that has a 12th order scheme? No, someone has a 12th order scheme, but then that'll start shifting us up there. So I think that's where we need to focus on. But the nice thing about this is now we're not just chasing around, oh, I wonder if I do this or do that, will it get faster? We actually have got a systematic way that we know exactly what we need to do to make it go faster. We're not wasting time chasing optimizations that are actually irrelevant or not going to get us anywhere. So we like systematic things that sort of like the inversion problem, like you want to know which direction you should be walking. Okay, now on to the stuff that you haven't seen, okay? So it's not a complete repeat of yesterday. So the other big effort in the project then is focused on this automated finite element system, Drake. So I think a few people here have used finite element. In particular, some people have used Phoenix and Phoenix and Dolphin. So these two projects are very closely related. Both of them use UFL, the Unified Form language, and this is a way of writing a finite element in variational form, and then solving it, so that's your DSL, and then generating code, finite element code for solving that. So this has got a whole bunch of stuff in there, like say, for example, someone's also asked me about PETSI earlier on. So this is a whole big structure. You write down a nice mathematical language of your variational form. So like physicists is very happy then, it's a very concise bit of code. And you specify, okay, well, this is the kind of preconditioning you should do in this system, and this is the type of solver. So this is quite nice as well, because you can simply look up the literature, see what the preconditioner is, and what the solver is, what the best solver is for that particular problem. It's very elegant, small amount of code. And then you apply the compiler. It generates the C++ code that's compiled. It runs and get the answer. It's all very easy, and it also scales very well. So both of those projects, like they run up to thousands of nodes on like Crays and whatnot. So they're not just TIE codes. They run on supercomputers. And so there's also this Dolphin adjoint. So this we touched on this yesterday. So this at the moment is integrated with Phoenix slash Dolphin. Like basically Dolphin and Phoenix are part of the same thing. It gets very confusing with their naming, but it's basically all the same thing. And this is it's basically integrated as well with FireDrake, but it's not good enough for production yet, but it's basically there. But this is basically giving us automatic differentiation support for this as well. So this is exactly what Felix was pointed out yesterday that we need, and you need to have it. This is interesting as well. So one of the big problems in finite element is just generating all of the basis functions. So this library here is actually used by lots of finite element libraries. It's used both in Phoenix and it's used in FireDrake. But there's a group of people, and actually one of the people on our IPCC, he spends half his time writing a new library to replace this. And that's largely targeting spectral element methods and higher order methods, where the existing framework is not so good. But you can see there's a lot of components here, but what it actually translates to is you up here, if you're the physicist and engineer, you write your specialized code where you're focused on your application very much. You don't care about all the stuff down here that worries about how do I actually get this running on all types of exotic systems and with MPI and OpenMP and everything else. And under the hood then as well, it's exploiting things like PETSI. So PETSI is an open source library for sparse linear solvers. And this gives you access to direct solvers, and like this is going to run on 1 million like cores, and you don't have to do any additional work. So this is the kind of space that you want to be operating in if you're interesting in developing new application. So this is what we're focusing on then, building an elastic wave equation solver on top of. So what does it look like? Well, say if we take the velocity stress formulation for isotropic. So once again, just showing that this is where our life is made easy. So Andres log. So he's one of the, like, you know, the Grande, what's the name for it? One of the godfathers, if you like, of automating all of this type of this automated computation. He was one of the original developers of PETSI, of Phoenix, sorry. So he basically wrote down, okay, well, this is what. So you can right away you can see here then it's actually simple to, like, this is what's really key. UFL, because it's DSL defined by this, is you're able to write it out. Like the compiler is able to read this. It knows what this means. It knows that it's an integral. Here you specify, it goes away and it solves it. If you want to change DG spatial discretization, well then it's only a call to a function where you define, like say U, in this case, tensor function space. DG is the element type, discontinuous Glerkin. So remember the compactness. We like the compactness about this. And then that's for first order. And then if we want for fourth order, like we just change the number to fourth order, and that's the job done. And then UFL is compiled down to low-level optimized C, targeting the specific hardware, and it's parallelized. So then our test case then is a verification problem. Like, you know, once again, it's simple eigenmode. Exactly the same problems we did for finite difference. And let me see, what are the things I want to talk about here? Well, you can see here for the discretization error, we can see the effects of running for the different schemes. So on the top here, this is the first order scheme. Oh, and this is different mesh size. Sorry, I should have explained. So this is the characteristic element size. So the mesh is fairly regular. All that we're doing is that we're reducing the element size. And then if the theory is correct, we should see it. We should see the order of convergence, like, you know, by measuring the slope of this line. So we can see that first order schemes, like, you know, they have a very low order of convergence, and you can see the error that it reaches. And basically, as you start increasing order, the convergence rate is faster, as you'd expect, and you achieve a much more accurate solution. So this is pretty much all that you expect. So the two diagrams here, they're actually the same. Just one is for velocity and one is for error. So it shows that everything has the order of convergence that you expect. So there's different ways of looking at this. So one way of looking at this then is if you say, okay, well, I can only afford to create a mesh of a particular size. So that's basically defined by this. Then if you follow up this graph here, it's basically telling you what, how accurate of a solution you're going to get. Okay, and then in terms of wall time, so this is the same story again, like a first order scheme versus for second, third, fourth order scheme. Here we see this number here, this is the element size. If we look here, this is our error norm, and then this is the wall clock time. How quickly is this thing running? So once again, the same way, if you want to adjust the dial, you say I want to solve to a particular accuracy. Let's say if you choose like 10 to the -5 velocity error R2 norm, then you simply follow it up through here, and basically you can see that the quickest route to a solution is a fourth order scheme. You can read off what the element size is and the time. So once again, it's just reinforcing by going up in order. What you're doing is you're reducing your time to solution. You're getting a more accurate solution, and it's requiring less memory. If you look at low order schemes, you can see here that the mesh size is tiny, and it actually, like, the results really, like, it doesn't give you very good accuracy. And I guess the question, even when we're actually applying this further downstream, is what accuracy we actually need to be solving the wave equation when we're actually using it in FWI. So there's going to be some experimentation there. So once again, I'm repeating a lot of what I said yesterday in terms of why you want to do it this way. Well, it's allowing us to do a lot of fast evaluation of numerical methods and optimization. So simply, it doesn't require a whole PhD student to try a new scheme. It's the kind of thing that you can quickly work your way through. So in this particular case here, we're just experimenting with an implicit solver. So in this case, it was passed into OPESCI, just the matrix, the entire matrix was assembled, and then dissolved with an iterative solver. And then this is like your regular explicit time stepping. And then this is just an optimization that's done by the compiler for ZR tracking. It eliminates a whole bunch of terms automatically before the code is actually finally compiled. So you can start doing these types of experiments and actually try to figure out what's the quickest way of solving this. But the important thing here is that it's facilitating you to do all these numerical experiments to figure out what's most efficient. So a couple of slides here. One of the big important parts of this is when the compiler is actually creating this code, what it's actually doing is creating a big, like what they call an AST, abstract syntax tree. And then there's a specific compiler then that actually looks at that syntax tree, and there you have all the operations with the multiply bys and all the terms of your equation. And it's going through that, trying to rearrange it, trying to eliminate everything that it can. If it knows that some of these zeros comes up to the equations, it's eliminating all of those. And it does a lot of, once again, it pretty much does a march through the optimization literature to figure out what it can apply to this tree of operations to optimize it. And this would also include like various local, maybe gather and scatter operations to create vectorization opportunities, like alignment, padding, and everything else. So one of the nice things here then is going back up here. What this means from a practical perspective is that while I might have one postdoc who's only focused on here, writing down these equations and trying out different numerical schemes for solving the elastic wave equation, whatever, efficiently. He doesn't care what the guy is doing down here to make sure that the code is rearranged and vectorized and everything else for a particular architecture. So you've got this separation of concerns. So I think not only is it sort of efficient, it basically means that the computer scientists are properly working with your geophysicists or whatever, and there's no crosstalk, or one doesn't need to understand. You don't have to teach geoscience or geophysics to your computer scientist. And maybe more importantly, you don't have to turn your geophysicist into an Uber hacker. I can partly explain why it works. I think this diagram, does it have enough information? So number one, I can simply answer yes. So one of the big projects that we have at the moment is we've got an open source CFD code called Fluidity, and like that's written in traditional Fortran 90. And at the moment, we're funded to basically rip out the main solver engine, so what's it behind, and just replace it with FireDirect. And already, so we have a bunch of stuff already implemented, and it's already much, much faster in FireDirect. And the point is, the original code was already quite good, but you have to make lots of compromises because you want to have a good design, something that's maintainable, like in terms of software, maintainability and extensibility are important. But it also forces you to make certain compromises associated with performance. Precisely, yeah, precisely. So like already, it was quite depressing actually when you see, because like me personally, I spent years working on Fluidity, and then once you actually kick this into action, the difference in performance was quite significant. But this is this is good, okay? I sort of felt bad all for a couple of weeks, and then I said, oh well, better evolve. But then in terms of data layouts and stuff, so I can get into a bit more detail if you want to chat about it. Am I going way over time? 5 minutes. Okay, well, the other note that I'll leave you with, then, to give you a bit more satisfaction with your question, is and maybe this is a general answer for a couple of people that are asking me about Phoenix as well, and what the difference between Phoenix and FireDirect is. One of the design philosophies in FireDirect is to have this notion of multiple layers of abstraction. So it's not just your DSL down to low-level code. You have your DSL, then it goes to this intermediate layer, which is PyOP2. So this is a much more general abstract DSL, and it only talks about data, like data sets and operations on data. It's very abstract, and you wouldn't normally choose to write anything on it. But it's the perfect layer of abstraction for computer scientists to start reasoning about and generating optimized code for, including what is the optimal data layout. And the other thing that's interesting as well is that, just maybe for industrial people as well, PyOP2, there was two codes developed together, PyOP2 and OP2, with Mike Giles in Oxford. So that code went into Hydra, which is the main turbine CFD code used by Rolls-Royce, and it's exploiting the same type of tricks basically to get a high degree of performance on GPUs as well as CPUs. So what I'm saying is, it's a pretty new trend. People have tried it in a few different contexts, and it's definitely winning. Okay, so let's get a move on. Okay, so then, like Mike was saying, I've got 5 minutes. So the other thing then I'll just touch on briefly. So this is one of the things, we're not actively applying this yet to the wave equation, but it's something like it's in our back pocket. Like it's going to be something interesting to play with when we get over the other development hurdles that we're dealing with. But we've a lot of years with adaptive mesh methods. And basically, to explain a bit about how they work, so you can do stuff like edge coarsening. So given a mesh, if you've got an error metric that's telling you that you have got too much resolution, then you can start collapsing some edges and removing that resolution. And what you're doing is you're removing degrees of freedom that are not really contributing to the accuracy of the solution. But this is important if it's speeding things up. Mesh refinement, I don't know what happened to my figure there. But basically that's the opposite. If you identify, actually I need more resolution in this area for whatever reason, then you split the edge. So these are all local operations that are done quite quickly. You can do swapping then of some edges. So this might be very good for aligning with some topographical features or some features inside your model. And it also allows you to generate very elongated elements if the features you're trying to resolve are highly anisotropic. And I guess, so the musings is, like, this has been massively successful in CFD and other multiphysics applications, where the key issue or the key blocker to like simulation is multi-scale, strong multi-scale features. And I think the reason why it could be of interest here is because, like for solving the elastic wave equation, there is going to be localized regions where you're incurring all of your cost. So this could be an opportunity to either, well, basically to adapt the mesh around that area, and maybe just have even a subcycling in your time step in that region. So suddenly it doesn't dominate your total cost. So in terms of where we're going with this, so I already talked quite a bit about what we're doing on the FD side. So I cover that there. This ADER DG, so this is the SciSol code that I mentioned that was at least a runner-up for the Gordon Bell Prize last year. We've worked on this for a while. It's really difficult to implement, to be honest with you. It's a tint order scheme. It's really causing us lots of headaches, so we have just given in and phoned up the guy who wrote the paper and invited him over for a few days at Imperial, so we can work through this and get it working. But this looks really, really interesting. We're quite excited about this. We're also looking at spectral element methods. So this largely requires the rewrite of FINAT. So this is something that Michael Lang, one of the members of our team, is working on doing. So these are two key things that we want to experiment with if unstructured matches are going to be at all interesting here. So this is FINAT. And in terms of our other focus, like to a certain extent, it has been good that we got bogged down with ADER, and this turned out to be more difficult to do than what we wanted. The guy's not going to turn up to Imperial for another month or two. So it's actually encouraged us to just go and actually look at actually using our stuff now for FWI and implementing something in the near term and see what it looks like. So I just finished up then with some links if you want to follow up on all of this. So you saw this before. So the Fire Drake and Phoenix and Dolphin, you can look up those finite element packages. So they're all open source, so you can play with it. If you want to take a look at the adaptive, so this work was originally funded by Fujitsu, actually. So that's also open source. You can play with it. And a couple of websites as well if you want to look at actually them being applied to some problems. That's all.